Assalamualaikum everyone. My name is Osama Khalid and I am a research assistant from Small Satellite Technology Research Lab SSTR under the National Center of GIS and Space Applications at IST. So today the topic of this lecture is the ICUBE CSAT Systems Engineering. Basically this ICUBE CSAT is a classroom satellite. So the outline of this overall is as follows. First, we will discuss what systems engineering is, what's its significance in terms of this satellite development process. Secondly, we will discuss what the small satellites are, basically the CubeSats and the pocket cubes. And then we'll mainly focus on pocket cubes as a classroom satellites, and we'll discuss the various subsystems and standards of these pocket cubes. In the third section, we will be discussing the systems engineering of the ICUBE CSAT, which was a classroom satellite developed by developed by the electrical EE17 batch of IST. So first, what is basically systems engineering? Systems engineering is an interdisciplinary engineering management process to evolve and verify an integrated life cycle balanced set of system solutions that satisfy customer needs. So basically, systems engineering is a discipline of engineering which involves the integration of systems. It is a robust approach to the design, creation, and operation of systems. The main aim of this system engineering is to integrate different interdisciplinary systems to work as a single unit. It involves the defining the common definitions and the standards of the system so that all the systems follow the same standard and can be integrated easily. So talking in terms of a satellite system engineering, there are three main phases. The first is that we identify the requirements and analyze them. This involves starting from the mission definition. We define the mission, what the mission will be, what's the orbit, what will be the payloads, etc. Then comes the preliminary design, in which we define the interfaces, we define the electrical mechanical interfaces, we define the subsystems, we break down the system in the whole satellite into multiple subsystems, and then comes the budgets and constraints, the mass, budget, power, link design, etc. Lastly comes the integration and testing of the satellite. So the first question that comes to our mind is, can students really design a satellite? Satellite development is an expensive process, both in terms of material as well as manpower. Very high quality human resources required in this field, as well as the equipment required to manufacture, and the components are quite expensive when we talk about the typical radiation hardened components. However, with the advent of these small satellites, the scenario has quite changed a lot. Talking about small satellites, the most common small satellite is a CubeSat. I think most of you may have heard what a CubeSat is. However, I will just briefly explain it here. So a CubeSat is basically a small cube-shaped satellite. A single unit is a 10 centimeter cube with 10 centimeter at height, length, and breadth. So this falls in the category of nanosatellites. There are multiple sizes. It can be a 1U, 2U, 3U, in which these subsystems are stacked. These single 1U units are stacked. These have become really popular due to their small size and quick development time, and most importantly, less cost as compared to the typical satellites. So CubeSats were basically introduced as a tool of education to impart the education and skill set of satellite development among the students. However, recently in the years, the commercial usage of these CubeSats has increased drastically. Large satellites are now being replaced by multiple smaller cube-shaped satellites, or you can say small satellites, which perform the same function but in a distributed architecture. This allows this has enabled to significantly reduce the cost of development, the time of development, as well as the failure chances have also been decreased, since the single point of failure, there is no single point of failure. You can easily replace any small satellite if any one or multiple of them fail. This as compared to a large satellite, where if it fails, the whole system or the whole function of that satellite will fail. So basically, coming towards pocket cubes, why we are talking about pocket cubes, or why we are taking pocket cubes as a classroom satellite project. Basically, CubeSats, although they are quite less costly as compared to the typical normal large satellites, however, the cost is not that much less that it can be used as a in classrooms or in colleges or among undergrad students to develop or to teach them satellite developing skills. Therefore, an even smaller standard of small satellites was introduced, named as pocket cubes, and these pocket cubes were basically much more simpler, much more smaller in size, having lesser subsystems of complex size, and mainly the weight and the launch cost were greatly reduced as compared to the CubeSats. So when we talk, here you can see in the figure that how small size a pocket cube satellite is. It's basically a 1 unit is a 5 centimeter cube unit. So now talking about that, why we choose pocket cube as a classroom satellite. Basically, the idea is to serve as a tool of education and impart the education of space technology among students. When students work on developing a satellite, they see all different aspects of the development, and this helps them to understand what real satellite or bigger satellite development process is. So this serves as an excellent teaching tool. So this ICUBE CSAT project, which was started, has a basic purpose that the basic purpose is that it provides a hands-on experience to the students for developing satellite subsystems. Secondly, it helps them to develop teamwork and coordination. Since the satellite is basically composed of multiple subsystems, multiple modules, and these are being developed by different uh, engineering students. Therefore, the purpose is to them the goal is to integrate all these subsystems into a single cube-shaped satellite. So this will require good coordination and teamwork among them in order to make it a successful project. And lastly, the purpose that this project serves is that it imparts multidisciplinary skill set among the students. Since satellite engineering is basically a uh, multidisciplinary engineering, it involves the electronics as well as it involves the structures and the controls, as well as science and propulsion. So therefore, all these topics of fields are basically covered when in the satellite development process. And when students develop a satellite, they learn concepts from all these engineering disciplines as well as sciences. So basically the final outcome will be that all these subsystems which will be developed by different teams of students will be integrated into a single cube-shaped satellite. Now now we will talk about the subsystems of a pocket cube. So there are multiple subsystems inside a pocket cube. As you can see that the basic is the structure, the mechanical part or the frame of this satellite, the pocket cube. Around this structure, the solar panels are placed, and inside this frame of structural frame, different subsystem boards are stacked over each other. Now these boards can contain the onboard computer. Basically, the onboard computer is the main brain of the satellite. It's the main controlling board. All the functions are controlled by it. It has a processor, some memory storage, and an operating system running on it, which controls the overall functioning of the satellite. Then there is a electric power supply board, which supplies power to all the subsystems and takes them from the solar panels and regulates these voltages and regulates the voltages. Then comes the communication subsystem. The purpose of this subsystem is to transmit the information and establish a communication link with the ground station. The antennas also integrate with this communication system and help in this communication link. Then comes the payload. Basically, payloads can be anything depending upon the mission of the satellite. They can be an imaging payload or a science payload or any instrument or some communication payload as well. So now I will discuss about different standards of pocket cubes. So basically, as discussed before, this idea of pocket cube was basically proposed in 2009 by Professor Robert in collaboration with the Morehead State University and the Kentucky Space. So as with the CubeSats, we have different sizes as 1U, 2U, 3U, 6U, 12U. So in pocket cubes, we also have 1P, 2P, 3P. So basically, as I previously told, a 1P is a 50 centimeter cube, a 50 millimeter cube dimension. Then 2P is slightly longer. It has a 2 single P units, and the third is the 3P, which has 3 units and 3 1P units stacked vertically. These can be seen in this figure on the right side. So now the pocket cube standards basically as you can see that here is a 1P pocket cube. So basically the mass of a 1P unit is around 250 grams. It has been defined as a standard mass. So basically one of the main differences between this shape and the CubeSat shape is that the pocket cubes also contain a sliding backplate. So as you can see here, the sliding backplate is at the bottom side and it has slightly different dimensions as compared to the other sides of this pocket cube. So the purpose of this sliding plane is for the ejection purpose. So when this pocket cube is deployed from the deployer or some other satellite, it slides using this backplate. So now talking about, there are basically two pocket cube standards known up to. These have been proposed by different institutes and organizations, and I will discuss them in the coming slides. So the first one is the PQ60 standard. Just as there is a PC104 form factor for CubeSats, there is a PQ60 standard for pocket cubes. So this standard basically defines the mechanical dimensions as well as the electrical interfaces of pocket cube. So here you can see the mechanical layout of this standard is given. The dimensions of all the sides and the stack holes and the stack connector is basically described. This header is basically the header and the receptacle connectors are shown here. These are basically 60 pin headers. That is why the name is PQ60. There are 60 pin connections on the stack header. On the right side of this figure, you can see that different subsystem boards are developed according to this mechanical standard. All of them contain the stack header, and the dimensions are also following the standard, and all of them are then stacked over each other and integrated. Now here is the electrical interface connection of this PQ60 standard. The electrical connectivity, the electrical connections which are defined are shown in this figure. There are 60 pins, and these include the power buses. Basically there are two protected power buses, 3.3 volt, and the other is the battery voltage. There are 6 switched power lines. Basically 3.3 volt lines and 3 battery voltage lines. Then there are 2 data buses, I2C and SPI. One is the reset line, one is the SS central general purpose input output pins. And all these basically are defined and need to be followed by every subsystem. The other standard is the PQ9 standard. So basically this, the purpose of proposing this standard was to introduce a smaller and much simpler interface as compared to the PQ60. Since this is a 9-pin connector interface, so it is much simpler and much smaller in size and volume reduced and much easier to integrate as well. The mechanical layout of this PQ9 standard is shown here. As you can see, the connector shown here is much smaller and simpler, and you can see how these connectors can, how the boards with different boards can be stacked over each other using this connector. The electrical interface is also very simple. One disadvantage you can say of this is that it does not provide much more options as the PQ60 standard does. However, at the same time, the size is also reduced and it is much simpler. Although the options are quite less in terms of the voltage lines and the data buses as well. So here is the pin configuration shown of the PQ9 connector. It contains the reset line. The data bus is basically, there is only a single data bus here, which is the RS485. 4 voltage lines are present, which are dedicated for different subsystems and payloads. And then there is a ground connection. So now I will be talking about the third part of this, the third section of this lecture, which is related to the ICUBE CSAT systems engineering. So this basically ICUBE CSAT project, which was done by the EE17 batch. So I will be discussing the main flow of how this system engineering of this whole project went. So the first thing, as I discussed before, is to we define the high-level requirements of this satellite. So the first thing is that you need to define what your mission is. You need to decide your mission. So the mission that was basically decided by this ICUBE CSAT, which was developed by this EE17, was that it will be taking a picture of IST. It was basically and then when the mission is being designed, you need to select the orbit, you need to select the payload as well. So this orbit was selected was the LEO orbit, and the payload was an imaging payload, which was an imaging camera, since the mission was to just take a picture during the daytime, once in a day. The other parameters that need to be defined, or the requirements that need to be defined, are the uplink downlink frequencies of the satellite. You need to define them beforehand. The modulation scheme that will be used by your satellite, and the memory requirements and other requirements that your satellite will be requiring for data storage. So these were basically the high-level requirements. Next we need to identify the system interfaces basically. So just talking about the system interfaces, basically there are three main approaches of integrating subsystems in a satellite. The one which is the most common is the stackable connector, which I have also discussed. In the previous satellites. The PQ9 and the PQ60 standards all follow this same configuration. They are basically stackable connector configurations. In this configuration, basically the satellites, different boards of the satellite subsystems are connected with each other by stacking them over each other vertically. This helps to reduce the size and gives a compact shape. The second is a backplane interface. So basically the backplane interface consists of a backplane, which is the main, you can say, a interconnecting board of the satellite. So on this backplane, as you can see, different boards are stacked vertically. There are some headers available, and all these boards are connected vertically on it, and then enclosed in a satellite structure. And the third is basically a CPLD backplane interface. So basically the difference between the CPLD backplane interface and a normal backplane interface is that a backplane interface that I have now discussed is a fixed interplane. The interconnects are fixed. The connections have already been defined. The electrical connections that are made on the PCB board are fixed and cannot be changed. However, with the CPLD backplane gives us an advantage of flexibility and reconfigurability. So it is the same, just the layout is the same as the backplane. It's just a backplane with different subsystems connected on the backplane. However, the backplane board contains a configurable programmable logic device, a CPLD, which can be configured during after integration. That is, you can reconfigure your routing in an interconnects of different subsystems as per the requirements of the mission at runtime. So this gives a great advantage of reconfiguration and optimization of resources depending upon different mission requirements as the satellite passes to different mission phases of its mission. Next thing is defining the system bus interface. So basically, in order to communicate information between different subsystems, some protocol needs to be defined. There are different hardware communication protocols, and I will be discussing the most common, some of the most common hardware communication protocols that are used by different small satellites. So the first one is the I2C, which is also known as the Inter-Integrated Circuit Communication Protocol. As you can see in this figure, this is a configuration of a I2C bus basically. There is a master device. This master device can be any of the system. Mostly it's the onboard computer of the satellite. And the slave devices are basically the other subsystems that are connected on the same bus. So basically this bus consists of two signals or two lines. One is the clock, the SCL, which is the clock signal, and the other is the SDA, which is the data line on which the data is transmitted. So as you can see, this is a synchronous communication as it involves the clock signal, and data is transmitted only through one wire. So it's basically a half duplex. It can only send or receive a single thing at a time. So in I2C, the slave devices are basically identified using their specific addresses. Each slave device is assigned a 7-bit address. So the advantage of basically this I2C is that a large number of devices can be connected. So if it's a 7-bit address, you can connect up to 127 devices, slave devices, to a single master device. So this really helps when you need to connect large number of sensors and other peripherals and interfaces with the master device. So another thing to consider is the pull-up resistor. Basically, the SD and SCL lines are open drain outputs. Therefore, you need to place the pull-up resistors on them in order to ensure the integrity of the signal on this line. So talking about the advantages, it's a highly flexible interface and it supports multiple masters. The speed is basically up to 400 kbps in normal mode. However, in fast mode, the speeds can go up to 3.4 Mbps as well. And the other main advantage is that it only uses two lines and multiple devices can be connected. So talking about the disadvantages, the speed is however slower than the SPI interface, which I'll be discussing next. And the other is that it requires some other components such as the pull-up resistor, which will obviously consume space on PCB. And the other thing is that as we increase the number of devices for complex system, basically some issues occur with the I2C, which data integrity issues, and the I2C causes some problems when there are many large number of devices connected to it. So now moving on to the next protocol, which is the SPI protocol. So it is a serial peripheral interface. As you can see here, that SPI protocol basically consists of 4 signals. The SCLK, which is the clock signal and connected to the clock of the slave devices. The MOSI is the master out and slave input. So this is basically the output line of the master, which is used to write or send data to the slave devices. And the MISO device is basically MISO line is basically the master input and slave output. So this signal basically is the input signal, and it is used to read data from the slave devices. So as there are different two different signals for read and write. Therefore, this is a full duplex system as compared to I2C, which is a half duplex. The main difference is that to note here is that the SPI involves a chip select signal as well. So basically, the SPI does not involve the addressing of devices. There are, instead of addresses, a separate select signal is used to select a particular device which is being accessed at the moment. So each device will be accessed through a separate select line. The talking about advantages, we can say that this is a simple in terms of that it does not require any addressing like I2C. The other main advantage of this SPI is that it is a very fast protocol. The speeds are more than 8 megabits per second, and it also supports multiple masters, and there are separate mesomosi, that is full duplex, as I have already discussed. However, the disadvantages are, there are also some disadvantages. The first most obvious disadvantage is that this is not a very highly scalable, since you will be requiring a separate select line for each subsystem added or each safe device added. Therefore, it's not scalable to add a lot of slave devices as well. Secondly, there is no flow control or no acknowledgement in this case, as in there is in UART or I2C, and there's only a single master here. Now let's move on to the third protocol, which is the CAN protocol. So the CAN protocol was basically introduced for automobiles. Basically, it is a very robust protocol and is used normally in high noise environments. So the CAN protocol, as you can see, is a two-line protocol. There are two signals, CAN high and CAN low. Basically, the CAN high and CAN low are differential signals. So these differential signals have high robustness and they are highly fault tolerant against the EMI electromagnetic interference. Another thing is that each device in a CAN system is basically known as a node. A CAN node consists of a microcontroller and a CAN, which consists of a CAN controller and a CAN transceiver. So basically, the CAN controller is mostly embedded in a microcontroller which supports the CAN protocol. Sometimes the CAN transceiver is also not needed if it is already embedded inside the microcontroller, but most of the time the transceiver needs to be added externally as it's not embedded inside. So this whole microcontroller and the CAN transceiver combine to form a single node. So the main advantage of this CAN protocol is that it is a very low cost protocol, since it greatly reduces the number of wires. Second is that it is a very it consists of built-in error detection. So in CAN, basically the the CAN protocol basically uses a technique which is called the lossless bitwise arbitration. This bitwise arbitration is basically used to resolve when multiple devices or multiple nodes need to access the bus. So based on some priority which is given in the communication message, the CAN protocol automatically decides which node needs to access the bus. The third advantage is basically the robustness of this bus interface. So the CAN interface basically uses 5 different mechanisms for detecting the errors. These are the bit monitoring, the bit stuffing, the frame check, the acknowledgement check, and as well as the cyclic redundancy check. And the last is the flexibility. CAN is a very flexible bus interface, since it is not an address-based communication, but rather a message-based communication. Therefore, we not need to assign any prior addresses to the nodes or the devices which are being connected. So you can remove or add any node anytime during the communication, and it will not affect the rest of the communication, since there is no protocol already established with the CAN node. And last is that it also consists of the multi-master and multicast features, which can be also be applied to the CAN protocol. Now talking about the disadvantages, basically some of the disadvantages are that the length of this bus is limited. There are up to 64 nodes which can be connected, and sometimes there is also an undesirable interaction between the nodes. So therefore, some precautionary measures also need to be taken in the software development of this CAN protocol. Lastly, it's the UART protocol. Basically, UART is the asynchronous. The previous I2 as compared to I2C and SPI, those were the synchronous protocols and involved the clock signal. UART is an asynchronous protocol. So another main difference is that UART is basically a one-to-one communication. Single device, it is connected to the transmitter of one is connected to the receiver of the other, and the transmitter of other is connected to the receiver of the first one, and the ground is basically common. So a very simple protocol. It only involves three signals, no clock. However, in order to recognize a message, there is a format for the UART message which involves the start bit and the stop bit, and some parity bit also for checking the errors. The disadvantage of this protocol is basically you cannot use multiple master systems and slaves. The data transmission is also data transmission rate of the UART is also quite less as compared to the I2C and SPI, and the size of the data frame is also limited to 9 bits. So, and the UART protocol can be operated in simplex as well as in half duplex as well as full duplex. It all depends on the user. So these were basically the system bus interfaces, and the satellite designers or the system engineering team can select any of these protocols depending upon the requirements of the satellite. So now I would be discussing about the different subsystems of the ICUBE CSAT. So the ICUBE CSAT, which was developed by the EE-17, consisted of these subsystems. So the subsystems which were mainly one was mainly the OBPU, which was the onboard processing unit. This was the main computing unit of this ICUBE CSAT. Then there was a CMOS sun sensor, which was the CMOS sun sensor was basically a sun sensor in order to determine the angles and the direction of the sun. This was developed using a CMOS sensor, a CMOS camera module of which along with the Arduino. There was also an imaging payload camera, an electric power supply board for powering the whole CubeSat. So the whole ICUBE CSAT. Then there was a communication module for communicating with the ground station. Then there were solar panel deployments and antenna deployment subsystems. Then there was an attitude determination and control subsystem. Basically, this attitude determination control system and the CMOS and sensor and magnetic router were integrated with this ADCS directly, which I will explain in the next block diagram. So this was the basic structure of this ICUBE CSAT. The I2C bus was selected as the system bus for communicating between different subsystems. The power lines or power, so the power was basically power lines were provided by the EPS board to each subsystem. And this ADCS module was basically the one team was basically designing the main ADCS module, which consists of the ADCS board and the reaction wheel, and the other two teams which were one was developing the magnetic talker and the other was developing a CMOS sun sensor. So this was integrated with the ADCS subsystem, and then this whole ADCS block was integrated with the rest of the subsystems through the I2C bus. So now coming towards the budgets and the constraints parts. So basically when designing the budgets and constraints, there are three main types of budgets. One is the mass budget, one is the power, and the other is a link design budget, which is a communication related to the communication system. So first, the mass budget is basically for a 1P pocket cube. Here what I have, the parameters that I have here written are for the 1P pocket cube. So for the 1P pocket cube, the mass should be less than 250 grams. So all the subsystem mass along with the structure and all this cube-shaped satellite should be less than 250 grams. And for this, you need to consider the packages of the selected components, the thickness of the PCBs, the types of materials you are using, especially the material of the structural frame. There are different alloys of lightweight and high strength alloys of aluminum, one of which is the AL707. There are also other 7075, etc. as well. Next comes the power budget. So for a 1P pocket cube, the power is basically less than 300 milliwatt average power is available. So you need to design your subsystems accordingly that they consume less than 300 milliwatt during the whole orbit time. So in this, you need to consider that each subsystem has different peak power consumption times. There's duty cycles of the subsystems need to be considered, that which subsystem needs to be continuously powered and which needs to be powered for just a little amount of time and then turned off in order to save the power. And then suitable margin percentage and the losses and decay considerations need to also be considered when designing this power budget. And coming towards this link design, basically the link design ensures that reliable communication link has been established between the satellite and the ground station. So the PR is here. PR is basically the power received at the transmitter, and it should be greater than a C minimum, which is a threshold, minimum threshold for satellite minimum power that needs to be available for reliable communication. So basically a margin is calculated, which is received power minus the C min, and this margin needs to be greater than 0 in order for the link to be closed and a reliable communication to be established. If this margin is less than 0 or the power received is less than C minimum, then the link is open and basically reliable communication is not possible theoretically. So this operation threshold C minimum basically depends on the modulation scheme that you have selected for your communication subsystem, the desired communication quality, what is the quality, the coding bandwidth, and as well as the thermal noise power. So now I'll be showing some examples of these power budgets. The first is this mass budget. So this mass budget is basically, as you can see, different subsystems are listed and different components and their masses are listed respectively. And all these masses all add to exact 250 grams mass. And this is basically a example mass budget from a pocket cube, which was named as UOMB SAT, right? Some university SAT, UOMB SAT 1. Similarly, as you can see, here is a power budget. Now this power budget was basically from basically an example CubeSat power budget. As you can see, there are different powers, average duty cycles, and listed here. So the power of each subsystem is listed, and the duty cycle is listed. So basically, as you can see here, that the onboard data handling system or the OBC, the duty cycle is 100% since it needs to be operated all the time. It needs to be powered all the time. So the power subsystem is also 100%. The ADCS, in the ADCS, you can see the ADCS board, the control board is 100% operating all the time, whereas the sensors are also operating all the time. However, the magneto-torquers or the actuators are only operating 2% of the time. And similarly, in communication, you can see the transmitter is only operating 10% of the time, while the receiver is operating 100% of the time. The receiver is operating all the time. Here again, example power budget from the UMB SAT 1. This was a preliminary power, where as you can see here, the different orbit times are illustrated. The APS is continuously operating. The communication system, the receiver is continuously operating, whereas the transmitter only 7% of the time, and the beacon is 10%. OBC is also continuously operating all the time. So this estimated was around 226, as stated above, that it should be less than 300 milliwatt. So it's less and it satisfies. The third and the last is the link budget. Basically, the link budget, as you can see, there is basically an uplink and a downlink. Uplink is the transmission from ground station to the satellite, and the downlink is the link of satellite to the ground station. So there are different losses and gains which are needs to be taken when designing a link budget. From the transmission perspective, there is a high power amplifier gain is added. There's a transmission loss of cable, the antenna gain is added. And then there in the path, there are antenna pointing losses, free space losses, and other pointing losses. And at the reception again, then there is an antenna gain and the reception losses of the cable, etc. So all these losses are added, and the gains are added, and then a link or a margin is obtained. So this is an example CubeSat, example link budget for a CubeSat. As you can see here, that the link margin is basically a maximum of 3.2 dBs and a maximum for uplink, and a maximum of 1.85 dBs for downlink can be obtained. So we can say that the link is satisfied and the link is closed, and reliable communication is possible. Now coming towards the last phase, which is the integration and testing. Basically, for integration and testing, there are different schemes that can be used. As you can see here, on the right side, you can see there is a single board, large board, on which different PCBs can be stacked, and all this type of thing is known as a flat set. And on this flat set, different subsystems are integrated together and tested before integrating them in the cube shape form and then launching. And the other scheme on the left hand side you can see is that each subsystem, there is a separate board for each subsystem, and all these test benches, or you can say the test boards, are then horizontally connected with the side connectors, as you can see here, the white colored connectors. So an example of this flat set is basically a Delphi pocket cube, which was a TU Delphi University's pocket cube was. And you can see there are these different subsystem boards, the ADCS board, antenna board, onboard computer, battery board, radio board. All of these different boards were tested on this flat set board, which contained different test points, and all these subsystems are tested on this flat set. So that was all from the system engineering point of view. Hope you have learned about the different system engineering point of views of this ICUBE CSAT project, and hope that it will help you in the future as well. Thank you.